So welcome. Today we will continue with our series on solution for the assignments of concepts of thermodynamics. So we will solve today assignment number 4. So let's begin with question number 1. So what they have mentioned is hot coffee in a well insulated thermoflask is shaken vigorously. That is some thermoflask is given and it is insulated. Okay, inside which we have a fluid which is coffee. Okay, consider it as a system. So we have to consider this as a system. So let us draw a system boundary and we have to tell which among the following statement is false. So what we are doing is we have given well insulated thermoflask and we are shaking it. So some external agent is doing some work on it. Okay, we can say it. And shaking is one kind of work for this kind of system. So work is done on the system and heat is added to the system means, so let me put it this way. So they have asked that which of the statement is false. Means work is done on the system. This is true. That means some external agent is doing work on this system. Okay. Then heat is added to the system. This is false. Why? Because the system is well insulated. Neither heat can enter into the system nor heat can leave the system. Okay. So this statement is false and internal energy of the system increases. So we have our energy equation like this: E in minus E out is equal to delta change in energy. So assuming that the changes in means this component consists of change in internal energy plus change in kinetic energy plus change in potential energy. Okay, I hope you know this. Then if changes in kinetic energy and potential energy are negligible, then we are left with only one component, that is delta U. So we have with us E in minus E out is equal to delta U. Okay. Then E in we can write that either energy can enter the system in the form of work or it can enter the system in form of heat. Energy can leave the system in form of work or energy can leave the system in form of work. Heat. Okay. And all this will cause changes in internal energy, which is nothing but U2 minus U1. So what we are getting here means the work is entering the system, means we are doing the work. Okay, the system is not doing work on the surrounding is doing work on the system. So this is work input to the system. Okay, so this is positive, means this is present. All these quantities represent what we can say some positive number because the sign is taken care of by this. Means we have already written this equation in the form that is E in minus E out. So we do not need to put extra sign for W in Q in. Whatever the number they have given, we have to just put the magnitude here. Okay. Then W in is positive. This is 0. Why? Because it is well insulated. I have told you. And we are not doing any work, means the system is not doing any work on the surrounding. So W out will be 0. And it is also 0. Okay. So what we have is delta U is W in and it is positive. So delta U is positive, means U2 minus U1 is positive, which is greater than 0. So U2 will be greater than U1, from which we can conclude that internal energy of the system increases. Okay. And since internal energy is a function of temperature, the internal energy at a final state is greater than internal energy at initial state. So we can conclude that temperature of the system rises. That's how, by following this argument and from this energy equation for the closed system, we can prove statement A, C and D are the correct statement. So only false statement we are left with is statement number B. So B will be our correct answer for this. I hope you got my point. Then coming to the question number 2 and 3. Okay, so what we have with us is piston cylinder arrangement. So the height given to us is 5 meter. Okay, a 5 meter high open cylinder they have mentioned with a cross sectional area. Area is also given, that is 0.2 meter square, and contains water at 20 degrees Celsius above. Okay, so we have water and temperature of water is nothing but 20 degrees Celsius, and here below with a thin massless insulated floating piston. and they are separated by a thin. So okay, so this piston is thin, means its volume, height, everything is negligible. Okay, so means whatever the means while calculating volume, we are going to neglect its effect. Okay, that's the only thing the thin is doing in this question. So we have thin, massless, means it doesn't have any mass, and insulated means it is not allowing the transfer of heat across these two fluids. Okay, so that's what this insulated is given here. Okay, then floating piston, so it can float, means it's not fixed, as shown in the figure below. Assume a standard G, that is acceleration due to gravity. We have to assume its standard value, and P naught, that is P naught is our atmospheric pressure. So the initial temperature of air, that is let's say at state 1 it is 300 Kelvin. Okay, and the initial volume of air, that is V1, it is 0.2 meter cube. Okay, now what is happening is now the heat is added to the air, okay, below the piston, so that it expands. Okay, so heat is added to the air, means we are adding heat to the air. So considering this as our system and drawing a system boundary like this, what we are doing, we are adding heat to the system, let's say Qn, which is uh, letting the air to expand. So it is rising the piston up, and the water it is leaving out of the piston. Okay, so pushing the piston up and causing the water on the top to spill over the edge, means the water is getting spilled over the edge due to the expansion of air, and this process continues until the piston reaches the top of the cylinder. So this continues till the air occupies the entire volume of the cylinder. Okay, means the entire water is spilled out. The process continues till that. So that's how, means state 2 is volume of air at state 2 is nothing but volume of cylinder. That's what they are trying to say. So what they are asking us to calculate, let me check. Okay, so we need to find the work done by the air to completely spill out the entire water from the cylinder. Okay, so we need to calculate the work done by the air to completely spill out the entire water from the cylinder. So for that we need to uh, calculate the pressure and volume, because we know that work done is nothing but integral PdV for the closed system. Okay, so we need to calculate the expression for pressure in terms of volume in order to get the work done uh, by the air to completely spill out the entire water from the cylinder. Okay, so from energy balance applying across the piston, we can write, means inside we having a pressure, say P, which is varying. Okay, and A is the area of the piston. Similarly, above we have a mass of the water which is varying. Okay, because it is getting spilled. So as the air is expanding, so mass of the water is getting varied. Okay, so mw times g is the downward force acting on the piston, and since the piston is massless, so okay, one more thing, there will be atmospheric pressure that we need to account for, which is nothing but p naught times a. Okay, because from hydrostatic law, at any point of, means at any given height in downward direction, pressure is nothing but p naught plus rho gh. Okay, so when we calculate force, we will get means upward pressure is something like this. So we will have pa, means applying force equilibrium in y direction, assuming this is as our positive y. So pa minus p naught a minus mass of water times g is equal to 0. So this is our force balance. So we can write pressure as p naught plus m water times g times area. Okay, so we can write is p is equal to p naught plus mass of water is nothing but volume of water divided by specific volume of water at 20 degrees Celsius times A times G. Because it is in meter cube and specific volume is in meter cube per kg. So at the end we will get mass in kg. Okay. So we can write mass of water because temperature of water is not changing because the piston separating the air and the water is insulated. Okay. So it is always at 20 degrees Celsius, means it is always in liquid state. So we can use specific volume in order to calculate mass. One more thing, from diagram we can see that volume of cylinder is equal to volume of water plus volume of air. Okay, we are denoting volume of air by simple V. Okay, so from here we can write it is P naught plus volume of water is nothing but volume of cylinder. Check, yes, volume of cylinder minus volume of air times G into specific volume at 20 degrees Celsius times A. So we have equation with us. So let me put it. So we have P is equal to P naught plus Vc minus V times G Vf. So Vf is volume of water at 20 degrees Celsius times A. So this is our pressure volume equation. So what we can observe from this equation is if we want to plot it, we can do it in two ways. Either we can integrate it by substituting the limit, that is V1 to V2. Okay, and what we will get is work done. Okay, or there is some another way, but whatever way we do, we need to calculate properties at state 1 and 2. So it will be laborious in both the direction. So let me show you this way, that is pressure and volume. And from this equation we can see that suppose it is of the form P is equal, matlab Y is equal to A minus Bx. How? Suppose we need to find out relationship between P and V, and we can see that volume of cylinder is fixed. Okay, and everything here is fixed. Only variable is V, and it is appearing with a minus sign in this equation. So as X increases, Y decreases. Means as volume increases, pressure decreases. So okay, so this line is sloping downwards. That's what we can conclude from this equation. Different point we need to calculate properties. So at state 1, what they have given, that is at state 1 volume is zero point 0.2 meter cube. Okay, suppose this is our state 1. So at state 1 volume is 0.2 meter cube, and what pressure is, temperature they have given. Okay, let me calculate from this equation. From this equation we can also calculate pressure. So P1 will be P naught plus Vc minus V1 times G Vf times A. Okay, so it is P naught plus, okay, the problem here is P naught value 101 kPa. Okay. Okay, so volume of cylinder is nothing but height of cylinder times area of cylinder. Okay, height is 5, it is 0.2, so it is 1 meter cube volume of cylinder. Okay, very simple. And V1 they have given, that is volume of air is nothing but zero point 0.2 meter cube. Water is at 20 degrees Celsius. Okay, and it is in liquid state. So we can mm, okay. So from the liquid table, means compressed liquid table, we can calculate, or not a compressed liquid table. Yeah. So water is in liquid state, means it is in equilibrium with the what we can say atmosphere. So it is nothing but is a saturated liquid state. Okay. So that's why we will calculate the uh, specific volume of water at 20 degrees Celsius at a saturated liquid state. Okay. So that's how we will get the value of Vf from table. You can get that easily. Okay. And area they have given, that is 0.2 meter cube. So this is known to us, this quantity. Similarly, we will calculate P naught. Means P naught is 101.325 kilopascal atmospheric pressure. So we will be having P1 with us, okay, in kPa. So I've calculated it and it's coming as 1 is 140.4. Okay, so that's how P1 is. That's the value of P1. That is 140.4 kPa. Now we have one state point with us. Let's calculate another one. So at state 2, what will happen? The pressure, let's say, so final volume will be equal to cylinder volume. Okay. So P2 will be equal to P naught. How? Because entire water will be spilled out, only air will left. That's why VC will be equal to, means V will be equal to VC, and this term will vanish, so that P2 will be equal to P naught. So pressure at state 2 is nothing but P naught, and volume at state 2 will be equal, it's simple, that is 1 meter cube volume of cylinder. Okay. So integral PdV is nothing but work done in moving from state 1 to 2. Okay. So this integral PdV signifies the area under the pressure volume diagram projected on volume axis. And this is trapezium. So we know how to calculate area of trapezium. It is nothing but half of P1 plus P2, that is sum of length of parallel side minus difference, uh, or we can say height. Sum of length of parallel side multiplied by height. Height in this case is nothing but 1 minus 0.2, that is V2 minus V1. Okay. So we have P1 with us, P2 with us, and this and this. So after all this, we will get our answer approximately to this value in kilojoule. Why kilojoule? Because this is in kPa. Okay, that is kilo Newton per meter square, and it is in meter cube. Okay, so kilo Newton meter, and Newton meter is nothing but joule. So we will be getting answer in kilojoule. Okay, so that's the first part. We have taken too much time here. So the third question is find total heat transfer to the air when all the water has been pushed out. Okay. So before doing this, one more thing I need to tell you, that is our system is doing work on a surrounding here. Okay. So we are getting work output out of our system. So the value that we got is, that is 96 point something. Yeah, 96.72 is our work output. It's in kilos. Okay. So from our energy equation that I have explained you in the first question, it is nothing but delta E, which will boils down to delta U. Why? Because the kinetic energy and potential energy terms will not be significant here, because they have not even mentioned them. And energy can enter in the form of work, and enter in the form of heat, or leave in the form of work, or leave in the form of heat. Okay. So is equal to delta U is nothing but U2 minus U1. Then we are not doing any work on the system. Okay. So it is 0. and they have clearly mentioned that heat is getting input, means we are supplying heat to the air. Okay, so Qn is the component relevant here, minus we are getting work out of the system. Okay, and remember all these things are magnitude because we have already means taken care of sign by this, means putting minus in front of energy which is leaving out. Okay, so you need not to put any extra sign in case of output, input, anything. Okay, just use this general equation and think just about either we are getting work from the system or we are providing work to the system. Okay, so when you do this analysis, then everything will be clear to you. Then Q1 minus W out. So there is nothing called Q out, or let's say there is, if any, U2 minus U1, because they are asking for total heat transfer. Okay, so let's say Q in minus Q out minus W, what is that? Out is equal to U2 minus U1. Similarly, so this is our total heat transfer, which is say Q total minus W out is 96. So bringing it to this side, 96.72 plus Q2 minus U1 is nothing but MCV T2 minus T1, because change in internal energy can be written like this: mass times specific heat at constant volume into change in temperature for calorifically perfect gas. And unless otherwise stated, we will always assume that the given gas is calorifically perfect gas. So for air it is nothing but 0.718 kilojoule per kg Kelvin, and T2 I hope we have calculated. If not, then we can easily calculate. Okay, everything is the calculation part here. So for mass, because at state 1 we know the pressure, we have calculated how. Volume is known to us. Mass is nothing but m, that will not change because it is a closed system. R for the gas is 0.287 kilojoule per kg Kelvin, that's also known to us. And temperature at state 1 is nothing but 300 Kelvin. So from this we will get mass as P1 V1 times RT1. Okay, so we have mass with us. It's very messy. So this is our governing equation in order to calculate heat transfer. Okay, highlighted it. Okay, we have mass with us. Then what else we required? Temperature at state 1 is given, but at state 2 we don't have temperature. So what we will do? Since mass will remain same, so P1 V1 by T1 is equal to P2 V2 by T2. P1 V1 T1 known to us. Okay, P2 is known to us. P2 is nothing but P0. V2 is nothing but volume of cylinder. Okay, that is volume of air at state 2. So T2 we can easily calculate from here. So after all the calculations, you will get answer as P. Okay, what you need to do is just put the values of all the variables that I have calculated above. Means I have told you how to calculate it, and after substituting the values here, you just need to do a calculation and substitute this value, means substitute all those values in this equation. So from that you will get total heat transfer as 181.99 kilojoule. Okay, all this thing will be in kilojoule. Then next question is, so a water filled with a reactor, with a water filled reactor. Okay, so this is our water filled reactor, say R, of volume 1 meter cube, is at 10 megapascal and 300 degrees Celsius, and it is placed inside a contaminant room. Okay, as shown in the figure below, it is placed inside some room. Okay, it is our reactor. Room is well insulated and is initially evacuated. Okay, so room is well insulated and evacuated. So well insulated means no heat transfer can take place. So Q is 0 for any change in state. Let me read the question completely, then I will tell you. So due to failure, the reactor ruptures and the water fills the contaminant room. So this is the state 1. When water is filled in the reactor, it is in compressed state. How I got to know that? Because when you will what I, okay, so when you will see a pressure table at 10 megapascal, okay, what you will observe that the saturation pressure that you will get na, it will be more than 300 degrees Celsius. Okay, so what is happening here? The temperature of the water that we have is less than the saturation pressure at saturation temperature at a given pressure. Okay, so this is a clear condition for the compressed liquid state. Okay, so that's how I concluded that water at the state 1. So this is say our state 1. So water at state 1 is in compressed state, and what other things we can do? Volume at state 1 is 1 meter cube for our water. From here, what we can do, we can calculate a specific volume at this state, or let me explain two more important things here. Okay, so what we have is a evacuated space. Okay, so when we rupture it, the expansion of water means the expansion takes place because it is in compressed state, so it will try to expand. Okay, so this expansion is not registered by a surrounding because our surrounding is evacuated. Okay, so we are not doing any work because the free expansion is not associated with any work. Okay, so work done will be 0 from state 1 to 2. Similarly, our system means this is insulated, so heat transfer is 0. Okay, so no energy can flow in either in the form of work or heat. Okay, so our component E in minus E out times delta U, or here delta E, and then KE, delta KE and delta PE will vanish as no information is given about them. So, and when we put that, means Wn plus Qn minus W out plus Q out is equal to delta U. Okay. So all these terms will vanish because of this, means from state 1 and 2 we can neither get work or neither do work. So all this will vanish. So left hand side will turn out to be 0. So what we'll have with us is delta U is 0, which means U2 minus U1 is 0, or we can say M times U2 minus U1 is 0. Since mass is not 0, so specific internal energy will be equal both at state 2 and state 1. So this is the relation which we will get after solving this. So what we'll have with us is U1 is equal to U2. So I've told you that this is compressed state. So from compressed liquid table, you can calculate specific volume at state 1, which will be equal to, let me check, 0.001397. Okay, it is 0.001397. Unit will be meter cube per kg. Okay, and specific internal energy will be equal to 1328.34 kilojoule per kg. In the gate exam, these values or table will be provided to you. Some more 1-2 values will be given other than this in order to just confuse you. Otherwise, some interpolation or means some intermediary values will be given. For that, you need to interpolate and calculate at this temperature and pressure. Okay, so all these things which can be done in order to just complicate the calculation, I have talked about it in my assignment number 1. So if you have any doubt, you can go through it. Okay, I will not waste time here just to explain that. So this is our internal energy. This is specific volume. Okay, then from this, what we can do? Okay, so we have, okay, we have volume with us and specific volume with us. So what we can do? We can calculate mass of water, which is nothing but V by V, that is. Okay, so we have 0.001397, and after calculation I will get mass of water as 715.82 kg. Okay, so I will get mass of water. Then okay, next thing is, so I need to read the question in order to solve this. Find the minimum volume of the room. Means what is the volume of the room so that the final pressure do not exceed 200 kPa. Okay. What will happen? It will rupture and try to fill the entire this room. Okay. So we need to have some minimum volume. They have so that the pressure, means the pressure of the water does not exceed 200 kPa. Okay. So this is the constraint that they have given. So at state 2, pressure is 200 kPa. And one more property that we have with us is U2, 132 at 0.3414. So at this pressure, we will calculate, when we will see that, then we will look from the uh, saturated pressure table, saturated water table. So what we will get means internal energy of the saturated vapor at 200 kPa is nothing but, let me check, it is 2529. Okay, 2529.49 kilojoule per kg. So clearly we can see that Ug is greater than U2 or U2, which means our U2 lies between Ug and Uf. Means it is a mixture of saturated liquid and saturated vapor at 200 kPa, and our water lies in this mixture state. Okay, at state 2. So that's an idea that we are getting from it. So we did this. We can calculate since U2 is with us, we will be Uf as x times Ug minus Uf. Okay, I made a mistake somewhere. Okay, so this is the equation. From table you will get the values of Uf, Ug, Uf. Okay, and U2 is with us. Okay, then what we need to calculate, what is the quality of the water at this state. So x will be equal to U2 minus Uf times Ug minus Uf, which you can find from table. It is written as UFG. Okay, in short it is written as UFG. If we expand it, it will be Ug minus Uf. Okay, so from here we will get quality, some value of quality. Okay, so once we have quality with us, we can calculate volume at specific volume at state 2, which is nothing but Vf plus x times Vfg. All these things we will get from table at 200 kPa. Okay, so we have V2 with us, some value in meter cube per kg. Okay, then so we have V2 with us, and mass we have already calculated. So we know that volume at state 2 is nothing but specific volume times mass. So from this equation we will get answer. So answer is C. So after solving you will get C as the correct answer. Okay, you need to just follow these steps that I have mentioned. Then next is, what is the volume of water that remained as a liquid after rupture of the reactor? Okay, so this is also an interesting question. So what they are asking is, what is the volume of water that remained as a liquid, okay, after the rupture of the reactor? For this we need to revisit the definition of quality, that is x is equal to mass, means in the mixture how much mass we have of saturated vapor. Let us denote it by mg. This is our definition. Okay, means in a mixture of saturated liquid and saturated vapor, what is a fraction of what is a fraction of saturated vapor in it out of the total mass of a liquid? Okay, so that's what quality signifies. So, and if we need to calculate the volume of liquid, what we need to do is, means mass of uh, gas, or we can say mass of vapor plus mass of liquid is nothing but equal to total mass. Okay. So hence, if x represent the fraction of mass, that is in a vapor state, so 1 minus x will represent the fraction of mass which is in liquid state. Okay. So when we will multiply it with this fraction, with total mass, what we will get? Mass of liquid. So once we have mass of liquid with us, and we know that our final state is at 200 kPa, so we know that is volume of specific volume of saturated vapor is nothing but Vf. So volume of liquid will nothing but equal to mass of liquid times specific volume of liquid. Okay, because our water is at state 2, and at state 2 it is in 200 kPa. So this specific volume will tell us how much meter cube of water per kg is in liquid state. Okay, so it is a per kg basis, and we know that from our quality and total mass how much mass of liquid we have. Okay, so when we will multiply it with specific volume of liquid, we will get the volume which is in liquid state. So D will be the correct answer in meter cube. Then next question. So air is in the rigid tank. So this is an important word. Rigid tank means change in volume will not be there. Okay. So change in volume will be equal to 0. At state 1, pressure at state 1 is 100 kPa. Temperature at state 1 is 300 Kelvin. Volume at state 1 is 1 meter cube. Tank is heated to 500 Kelvin at state 2. So at state 2, T2 is 500 Kelvin. V2 is equal to V1. Okay. Now at state 3, what is happening? One side of the tank is acting as a piston. How this is happening means we do not need to bother about it. But what they have mentioned is means from state 1 to 2, it was constant volume process. But now from state 2 to 3, what is happening? One side of the tank is acting as a piston and letting the air expand slowly at a constant temperature. So it is isothermal process because it is letting the air expand slowly at constant temperature. They have mentioned it to state 3. So volume at state 3 is nothing but 3 meter cube, and temperature at 2 and temperature at 3 will be equal to 500 Kelvin because it is isothermal process. So we need to calculate pressure of air at state 2 and 3 respectively. Okay. So since it is a closed system, mass will not change. Okay. So pressure we need to calculate. From ideal gas equation we know that PV is equal to MRT. Okay, then from state 1 to 2, we have constant volume, that is V1 equal to V2. Mass is not changing, R is not changing. So we can take a ratio, that is P1. We can write one more step, RT1, and P2 V2, MRT2. Similarly P3 V3, MRT3. This is at state 1, state 2, state 3. So for 1 to 2, we can take a ratio which will be equal to P1 V1, P2 V2 is T1 by T2. Okay, so volume is constant, V1 and V2 are equal, so they will cancel out. So P1 equal to P1 by P2 is equal to T1 by T2. So P2 will be equal to T2 by T1 times P1. From here we will get P2 because we know T2, T1 and P1. Okay. P2 will be known to us. Then at state 3, we can again take a ratio P3 V3, P2 V2, T3 by T2. Okay, so T3 by T2 means T3 T2 will be equal because isothermal. Okay, so let me erase it. So it will be clear to you. So P3 V3 is equal to P2 V2. Okay, so that's what the equation for isothermal process undergone by ideal gas, which is nothing but PV is equal to constant. So you need to remember this, okay, for rest of your journey, because you will be using it so many times. So it is applicable for ideal gas undergoing isothermal process. Ideal gas is a very important thing here, because you can't apply it for any isothermal process. Only when the fluid is ideal gas you can apply it, and if that ideal gas is undergoing isothermal process. Okay, so P3 we need to calculate. P2 from this we have calculated, that is T2 by T1 times P1, and V3 is given as 3 meter cube. Everything on right hand side is known to us. Just we need to calculate P3 by plugging this values. So after all this you will get C. Okay, just put the value, you will get all the answers. So done by the air. So 1 to 2 and 2 to 3. What is happening in 1 to 2? Or for a closed system we can write integral PdV as a work done. Okay, so from 1 to 2 volume is not changing, means TV is 0. Okay, so work done will be 0 because the tank is rigid. And in 2 to 3, one side of the piston or cylinder is acting as a piston, and we are getting a isothermal expansion process. So what so PV is equal to constant. How we are getting this? I have explained you in the above equation. From the ideal gas equation, PV is equal to MRT, and MR is constant for a given gas. So for isothermal, T is constant. So from that we will get PV is equal to constant. Okay. So when PV is equal to constant, we can plug here. That is P we can write as C by V times TV. So after integrating, it will be, so suppose limit of integration are from V1 to V, or put the limits. It is from 2 to 3. So V2 to V3 expansion is taking place. So it is ln. So C will come out as it is constant, and integration of 1 by V is ln V. So it will be V2 to V3. Okay. So W will be equal to C times ln V2 minus ln V3. So C we can write as means either PV is equal to constant, na? So we can write P1 V1, P2 V2 is equal to constant. Okay. So whatever you may find convenient, you can write it as like this. And we know from property of logarithm, that is ln A by B is nothing but ln A minus ln B. Okay, so here we will use that V2 by V3. So once, since P2 P1 is known to us, V1 is known to us, V2 V3 is known to us, we will get W23 as P1 V1 ln V2 by V3. This is the equation of the work done by the air undergoing isothermal process. So total work done is nothing but W12 plus W23. W12 will be 0. Why? Because tank is rigid at that time. And W23 will be equal to P1 V1 ln V2 by V3. Just plug in the values of all the parameters, then you will get B as a correct answer. Now coming to the 8th question. Total heat transfer during the process. Okay. So above what we get is means, okay. So the work done that we got is work done by the air, means work done by the fluid or the air in the cylinder on the surrounding. How? Because air is expanding. Okay, so in expansion we get work done by the system. So W we got above as 183.106 and it is out some value 108 whatever we got above in kilojoule. Okay, so this is the value that we get, and we need to calculate total heat transfer during the process. So same logic that we are using, I will not tell again and again, it will just waste our time. So E in, E out, make a habit of writing equation like this so that you will never miss out any term. Okay, so Wn, there is nothing called Wn. Q in minus Q out will be Q total or Q net minus W out is 10. Let me check what is 183. Sorry, is 183 point something kilojoule, and delta U is nothing but M CV T. Okay, T3 minus T1 Q total 183 plus M CV T3 minus T1. Okay, so since uh, since delta U, or we can say internal energy, is a mm, point function. Okay, so since internal energy is a point function, so we can directly write it as once difference between T3 minus T1. Okay, we do not need to look at the state 1 to 2 then 2 to 3. If we do like that also, we will get the same thing. So let me show you how. Suppose delta U 1 to 2 plus delta U 2 to 3 is delta U total. Okay, so it is MCV T2 minus T1 plus MCV T3 minus T2 delta U. Okay, you take MCV common, T2 minus T1 plus T3 minus T2 delta U. So it will turn out as T3 minus T1 MCV is equal to delta U. That's what I have written here. Okay, so M I hope we have calculated. If not, you can do that easily, or they have given it. Okay, they haven't given it. So from state 1 you can easily calculate P1 V1 M R T1. Okay, by using this equation, because P1 V1 R T1 everything you know, so you can easily calculate M, and since you have M with us, M with you, so and T3 is known to you, T1 is known to you, and CV is nothing but 0.718 kilojoule per kg, unless otherwise given. You have to kilojoule per kg Kelvin, unless otherwise you have provided a particular value of CV or any information about the CV, you have to use this value for air. Okay, so this is for air, so be careful while using it. For this question we will get total heat transfer as option A after substituting all the values. Okay, then coming to our final question for this assignment, that is, suppose we have a tank A which is having volume say 1 meter cube or VA. Okay, volume 1 meter cube, 1 meter cube contain oxygen at 300 Kelvin, pressure is 300 kPa. Okay, and another tank we have B which contain mass of oxygen is 5 kg, temperature of oxygen is 400 Kelvin, pressure of oxygen and tank B is 400 kPa. Okay, two tanks are connected by a pipe. Okay, in this kind of question, one more thing I would like to say, I would like to add, that is, Suppose you might be thinking, when I will be solving for state 2, I will be adding volume of tank A and volume of tank B. And some of you might think that what to do with this pipe. So in this first thing is, they haven't given any information about the pipe, means the dimension of the pipe. So we are not in a position to calculate anything about the pipe. Okay. And if in a exam they are providing any information regarding the pipe, then you have to calculate it. Okay. uh, Means you need to take into account. But in such kind of cases, what happens is, the dimension of these tanks are much larger as compared to this pipe. So it is a fair assumption to neglect the dimension of the pipe while calculating volume. Okay. So that's the part. And similarly, one more thing, they haven't mentioned anything about means work and all. And means they need to mention what we can say explicitly about the work, but they haven't did it. And also they haven't mentioned about the rigidity of the tank in this question. But we will still going to assume means the tanks are rigid, because it will be very difficult for us to solve it if we don't assume it. Okay. So means if it comes in exam, then they will definitely give you that tanks are rigid. Okay. But here they haven't given. That's their problem. So at initial state, we have provided the properties of the oxygen within the tank A and B. Then two tanks are connected by a pipe and a valve which is open along, allowing the whole system to come to a single equilibrium state with the ambient at 30 degrees Celsius. So at state 2, temperature is 30 degrees Celsius, which is 30 plus 273.15 will be this. It is 303, I think. Okay. So this is the final temperature. So they are asking the final pressure of the oxygen. Okay. So from this information, what we can do is, we know that PV is equal to MRT. So we will get MA after solving this. Okay. Similarly from here, okay, it is PB, VB, MB, RTB. Okay. After solving this, we will get PB. Okay. So everything about state 1 is known to us, because we are having oxygen with us. And one more thing, the R for the oxygen is nothing but universal gas constant by molecular mass of the oxygen. Okay. Oh, means you need to remember the, because they haven't given the R value for this, means, so, and also they haven't mentioned the molecular mass of the oxygen. So you need to remember molecular masses for some of the gases like oxygen, CO2, nitrogen. Okay. So that you won't be in any trouble at the time of exam. Okay. Now, what we need to do, we need to calculate the final pressure of the oxygen. Since at the final state, what will happen? The total volume at state 2 is nothing but volume at state 1, volume at state 1 in tank A, and volume at state 1 in tank B. So, similarly, final mass will be mass in tank A plus mass in tank B. Since mass is with us, volume is with us, temperature is with us. So, P2, V2, M2, R, T2. Okay. So, from this, we can calculate P2 as M2 RT2 by P2. Sorry, by V2. Okay. So M2 we have calculated. R, I've told one thing about R. And T2 we have 303.15. Okay. And V2 is okay, VA plus VB. Okay. From here, we can calculate the, what we can say, the final pressure of the oxygen. Okay. That is the pressure at state 2. And it will come out as D. Once you will solve, you will get this answer. And let me also tell you value of R. So R here is so characteristic gas constant for oxygen is nothing but 0.2598 kilojoule per kg Kelvin. Okay. So you can remember it, or either you can remember the molecular mass of the oxygen and divide it with with universal gas constant. Okay. So you will get same number. Then okay. So nine question is done. Then final question is the amount of heat transferred is. So thing that I've told you that tanks are rigid in the beginning will help you to solve this part of the question. So since tanks are rigid, we can't get any work output or we can't do any work on the system. Then amount of heat transfer, that is E in minus E out, is equal to delta U. Okay, so work transfer can't take place. So whatever may be the change in energy, it will be due to the flow of heat. Okay, so the energy in energy out, it will ultimately lead to Q total, and delta U is nothing but U final minus U initial. Okay, so Q total, U final is mass at state 2. Okay, and internal energy at state 2 minus Q initial is mass in the tank A at state 1, internal energy of tank A at state 1, plus mass in tank B at state 2, internal energy in tank B at state, sorry, at state 1. Everything here means this is at state 2 and this is at state 1. Okay, so we know for ideal gas U2 means U can be written as CV integral CV dt. For calorifically perfect gas we can write it as CV T2 minus T1. Okay, so it is CV T2 and the reference temperature. Okay, delta U. Okay, so M2 is equal to CVT2 minus this MA CVT1 plus MB CVTA1 TP1. Okay, so M2 is known to us, MA is known to us, MB is known to us, T2 is known to us, TA1 is known to us, TB is known to us. Problem here is with CV. Okay, so one more equation we have, Cp minus Cv is equal to R for an ideal gas. Okay, so and also Cp by Cv is equal to gamma. Then we can write from here we'll substitute the value of Cp here, so we'll get gamma times Cv minus Cv is equal to R. So Cv will equal to R upon 1 minus gamma. Since R I have told you 0.2598. Okay, Cv is equal to 0.2598 and gamma for diatomic gases. Okay, sorry, it is gamma minus 1. Okay, it is 1.4, so it will be 0.4 because 1.4 minus 1. So let me confirm it whether we are getting same thing, 0.2598 divided by 0.4, getting it as 0.6495. So let me confirm it from set matching Yeah, it's near about same. They have used the value as 0.66 something. Okay, so we are getting almost same value. So this is how, if CV is not given, you need to calculate this. Otherwise, they will provide you the CV, the question itself. Okay. So after doing all this stuff, you will get answer as C. Okay. So what this negative sign is signifying, that means, suppose if we expand this equation, we can expand that Wn plus Qn minus W out minus Q out is equal to delta U. Okay. So delta U is coming out as negative, means Q total is coming out as negative, means change in this side means RHS is negative. Okay. So what we are getting, this is 0, this is 0. Q in minus Q out is negative. Okay. Means heat is leaving the system. That is what it is signifying. Okay. Because Q out term is, this is negative, means Q in minus Q out is less than 0, which means Q in Q out. That is, Q out is more than Q in, means heat is, net heat is leaving the system. Means amount of heat transfer is out of the system. Okay. So that's what this negative sign signifies. So thanks for watching. And in case of any query, you can connect with me on LinkedIn. I have provided my URL in the YouTube description, and also you can join my Telegram channel. Thank you.